This is about automatic gain control, AGC, being done digitally and with a feed-forward internal system configuration. Here's a model to explore this issue. This is a Simulink model making use, in fact, of DSP Speedster, which is a lab kit you can get available from DSP Creations, and it sits on top of Simulink and gives us some nice features. I'm going to be going across the top of this model in this chain right here, paying very little attention down here, so you can put this out of your mind for now. This will be a sort of footnote at the end. What happens is I've got samples of waveforms, in fact chunks of them coming out every half second, because these are sampled at 8 kilohertz, and they're going to come in a continuous flow, and I have immediately here a block which spoils those waveforms and causes me big trouble. And the rest of the chain up here is attempting to undo the spoilage that's taken place here. The hero of the operation is the automatic gain control block, which is going to try to combat the effects here. I'll first just simply come straight through this block and come out with the replica of what goes in already spoiled, and come over here to get some familiarity with this, coming up through the input over here and going into the white port of this scope, and furthermore going on up here to where I can listen to the effect. So let's first listen to it.
The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric. The discrete Fourier transform of a real-valued signal is conjugate symmetric.
Okay, that's enough of that. Quite disturbing sort of surges and fades which are coming along. We can look at the picture of this, and we can see that, of course, this half-second waveform segment that we've got here is sporadic in nature, sort of bursty, sort of waveform typical of speech, with some gaps and some very low amplitude areas. It makes you sort of wonder when you look at speech if we couldn't make use of some of these downtimes in between to do something. And in fact, that's what we are going to try to do in trying to ameliorate these effects of the fading that was going on that we were listening to. Well, fading is an important effect which plagues a lot of communication systems, particularly voice communications. People like amateur radio operators and so on, who have signals going through atmospheric effects which cause great problems for them, and AGC comes to their rescue sometimes. Of course, true fading is very complex and random and all the rest of it, and so what we've got here imposed on our waveform is not only the sporadic nature, but also some weighting which has been put in here, and I'll show you what I've done. I've got here a linear rundown following on to a small plateau, and here's the point: it's all multiplicative, so the original waveform is not having any noise added to it or anything else like that. It's just getting this multiplication operation which is most inconvenient and most disturbing. Of course, if we were in the fortunate situation of knowing what this multiplication factor is, all we'd have to do would be to divide it back out and we could recover the waveform. But of course we don't have that knowledge, and the AGC block has to operate in ignorance of whatever might be concocted here, not just our simple little model. This block has two external parameters coming in. One is N. It's to do with the power measurement, which is one of the important concepts of what we're doing here. And the other is boost, which is coming in, which is involved in the clipping, which is one of the other important activities that we're going to do inside this box. So let's go inside underneath that mask, and we see our signal flowing in from the left. We come in through a DC notch filter to get rid of DC, and of course AC coupling is a thing that we often do in audio to get rid of any dominating constant or low frequency content coming in, and we work with that from now on. And notice the structure of this. This is a flow of several little fiddly blocks that we've got to go through, and it comes up and multiplies the original. So The incoming signal is getting treated to some feed-forward processing. Now, what is that? Well, here our parameters coming in here. 50 is coming in on this line, 20 is coming in on here. And in the case of the sliding power block, just to remind you what that might look like, I'll go underneath here. And I notice that there's a squaring operation and then a 50-point moving averager. So what's happening is I'm getting slices of the waveform, power measurement, 50 of them contributing to each point, and then the whole thing sliding. Moreover, I go through a square root block, so this is really RMS short-term total power being measured right out here. This is possessed by the incoming waveform. Now, my contention is I don't too much like this, and I would like to redistribute the power in a way that will help me fight against the fading. Not at all an obvious thing, quite a sort of sophisticated thing when you come to think about it. So I'm going to ultimately come over here and do a reciprocal operation. The idea overall is that where the power is initially small, I would like to inject large power in what goes out. If the power comes in large already, I would like to just inject just a little bit, and this will then carry out a redistribution of the power makeup of the signal. So we're reaching deep into the guts of the waveform and pulling it out. The fluff which is inside, we're pulling it out and making it bigger. And here's how we do it. First off, we're going to have to do some deciding how deep we can go with this clipping operation. There's a clipper right here, and if we're not careful, we'll clip it so low, the waveform will come in so small, like close to 0, so that when I go through a reciprocal operation, I'll be having 1 over 0, I'll have infinity, and I don't want that. So I've got to set a reasonable clipping level below that, and all of this is over here is concerned with that effect. And it involves this boost parameter, which is my other thing. Well, every n samples, I reset this running maximum calculation. Because I have no idea how big is big and how small is small inside my waveform, I have to interrogate it with this block right here. And so over 50 samples, I found out who's the biggest in that block of data. And then using the factor 20, let's say, it's easier to understand this boost, I take 1/20th of that maximum and let that be the low clipping level. So this protects me from going too low. And then of course I reset this, and each 50 samples I've got a new clipping level, and this clips. And what happens is I pass on through this clipper everything which is big or bigger than the low clip level. I mustn't go to 0 because here's my 1 over x kind of calculation. So here it is then. I'm always pumping up here. Big numbers when these are small, small numbers when that over there is big. That's the whole punchline of this thing. And I can see that clipping because I'm taking all these to the outside, so I've got these terminals available, and here they come across. I'm going to first look at this scope right here and just get a feel for that. Notice there's some big stuff that happens because of the silence, and there's other times in which I'm getting small white waveforms, and corresponding times I've got large yellow waveforms. The yellow one is my reciprocal calculation coming out. So when one's big, the other is little. And this then gets inherited by the waveform which comes out over here. And now it's going to be time to look at that because it comes out of my AGC output block. That's after I've imposed this onto the incoming waveform. And it's going to be this yellow plot on this scope right here. Well, that was the white one, so let me restore the yellow one and get rid of the white one. Now, instead of being so sporadic, the power has been distributed throughout the waveform, as you can see. And it's a massively different looking thing. The question is, this strange thing which no longer looks like speech, is it going to sound anything like speech, or just what? So this is going to be me now listening to that coming out.
The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric. The discrete Fourier transform of a real valued signal is conjugate symmetric.
Well, if you ask me, that's a whole lot better than the input, because although it's got some strange sort of roar going, it doesn't have
the discrete Fourier transform of a real valued
that
signal
fading
is
anymore.
conjugate.
I've made a massive impact on the fading by redistributing the power, and while it might not be the most wonderful looking waveform or sounding waveform, it's certainly intelligible, and it has removed the fading. The question is, have I actually redistributed the power in the way that I've argued? And so I'll actually have a look at that. I don't want to have too many scopes going on here, so now I'm going to make use of this measurement down here, and this block is going to take the outcoming power from this, and it's going to come over here and allow me to contrast that on this same scope with what came in the original waveform. That was power in is going to come straight through. So let me look at that here now. I need to restore both waveforms. Yes. So now the yellow one is the original power that came in with the fading waveform. And of course this is time. This again is 1 second's worth of data. And these are the little 50 sample segments which are being calculated, resulting in the white waveform, which is, as you can see, much more uniformly distributed throughout time. And that's what's then contributed to this struggle against the fading and the improvement that our dear old AGC block has been able to impart.